to a new chapter. This is about the equivalent elements and circuits and superposition. So this equivalent concept is important in the analysis, circuit analysis. So we are going to start with this equivalent circuit concept explanation first. Let's go in details. What is equivalent circuit? Assume that part of a circuit is equivalent to an other one. Part of a circuit is equivalent to other one, which has two or more elements connected together somehow. When equivalent circuits replace with the original one, the other elements, those not related to the equivalent circuit, currents and voltages do not change. Maybe it is not that clear when you read it first time, but if you read this one by looking at this picture as well. So in here on the left hand side circuit, we've got E, F, G elements in a black circle. We are saying if there is an equivalent circuit to these E, F, G elements, so it is a H circuit as a red square here. So what we are saying, if we replace those three elements with this H1, which is done here, the other elements within the circuit, in the original circuit, the other elements were A, B, C, D, and in this circuit, the other elements, that means those not included in the equivalent circuit. So these A, B, C, D in both circuits are not included in the equivalency. Those elements, current and voltages do not change, we are saying. So that means current of A, B, C, D, A, B, C, D here. So this circuit and this circuit, you're going to get the same currents, and voltages are going to be the same as well for these elements A, B, C, D. So that's equivalency. That's why we are saying this is equivalent, because the rest of the elements, current and voltages, do not change. This equivalent replacement do not affect the other elements, current and voltages. So we will be using this concept now for the analyzing these circuits, how we are going to use them. So there are some applications. One of the serial equivalence, we're going to use it. Parallel equivalency, we're going to use it in the analysis. And we're going to explain how we use this equivalent concept in comparing the practical elements and theoretical elements. And a completely new equivalent concept of which name is Thevenin-Norton equivalent circuit we will be using in the analysis, and the application of these Thevenin equivalent circuits, and the last one is the superposition theorem. Let's start with the serial equivalent circuits. So first of all, what is serial connection? Serial equivalency, serial connection first. If one of the terminals of the two elements are connected on a node where there is no other connection, then these two elements are serially connected. This could be extended to more elements. Now what we are saying, keep that definition here and then that circuit here. We are saying in this circuit, A and B elements are connected as serial. According to the definition of serial connection, one of the terminals are connected to a node, and there is no any other element connected to this node. There is no any other element. So only two elements are connected to this node. Then these elements are called serially connected. For example, on this circuit, D and E or D and F is not connected in serial, although one of the terminals are connected together in this node, but there is another element also connected to this node. So E connection makes it not serial connection. So you could say that D and E, E and F, and D and F are not connected in serial. But you could say that A and B are connected in serial. B and C are connected in serial. A and C, not two terminals are connected together. A and C is connected together. We won't say that. The equivalent of serially connected elements could be same type, one element. For example, serially connected resistors equivalent is another resistor. So this equivalency that we are talking about, if these are same type of elements, then serial connection gives you the same type element. Equivalent circuit of a circuit could be serially connected elements. For example, Thevenin equivalent circuit. Equivalent circuit of a circuit could be serially connected. So we are saying more than one. A circuit which has got many elements in it can be replaced with a serially connected elements. So serial connection, so we are talking about serial connection now, that's why we said there is an equivalency of which name is Thevenin equivalency. This is end up with a serial connection. So we will see that, so don't worry now. Some of the serially connected elements may not have equivalent circuit. For example, a resistor and a dependent source. So if this is a resistor and dependent source, we cannot replace those two elements and put just one element. So there is no equivalency like that. But if this is a resistor and this is a resistor at the same time, then we can replace them and then put just one element there. We could do that. Position interchange of serially connection elements would not affect Kirchhoff voltage law, current law equations. What we are saying here, if you replace element A with B, so replacing those two positions replace. So when you change this, if you do this, we are saying Kirchhoff current law and voltage law equations do not change, because what you're going to write the equation for this node after you change and before you change is going to be the same. And voltage, if you are writing the Kirchhoff voltage law, so voltage of this one addition with the voltage of this one, if you replace them, voltage VB plus VA it is going to be. This is also means equal to VA plus VB. So since these equations are not affected, so you can say that you can replace serially connected elements, then there will be no change. So some of the general rules that we could say for the serial connections we just said. Let's come to an example now. Here in this circuit we are seeing 7 resistors. They are all connected in serial. So we could prove that we can replace all these resistors with just one resistor, of which resistance equal the summation of these resistors resistance. So this is that one then. How we are going to prove it? Easy, because from the equivalency we know that when you replace this one with this one, this current is not going to change, because this current is equal to negative of this independent voltage source, which is outside of your equivalency circuit. So we are going to prove that we could have these currents equal when you replace these resistors. How we are going to prove it? It is written here. This is Kirchhoff voltage law equation written for this one, and then you can use the resistors definition relation and transfer these voltages to currents as it is seen here, and then you're going to see that the I current here will be the same for all the resistors. So if you choose this resistor current reference from left to right, left to right, left to right, downwards, right to left, right to right, right to left, then all these element resistors are going to be the same for this I. So this is done here. If you put the I parenthesis, so this is summation of the resistors is going to come. Now we are saying this is, if I say that this is equivalent circuit resistor, it's going to be the same Vs equal. So that means you can replace all these resistors, summation of this resistor with the equivalent resistors. Nothing will change. That is this. So that is the general, and that's the application of this general rule. This is n resistor connected in serial if it is just 7 only. So that is the equivalent resistance value. Conclusion. This current, I current, whether you are in this circuit and this circuit, does not change. And voltage, that voltage, Vs and Vs here, does not change, independent voltage source. Current of the resistors in serials are the same. So we just said if you write the Kirchhoff current law equations for these two resistors, they're going to be, currents are going to be equal. So this is a conclusion, so you could use that information anytime you need it. Once the equivalent replaced with two resistors in serial, KCL equations will be reduced by 1. So assume that these two resistors are connected in serial, and if you replace these two R1, R2 resistor with its equivalent, that is R1 plus R2, just one resistor, this node is going to disappear. So you're not going to write the current law equation for this node. So you reduce the Kirchhoff current law equations by 1. Non-standard resistor value resistor can be set by resistors in series. How? Assume that this is 1 ohm and that's 5 ohm, and you need 6 ohm resistor which is not available in the market. So if you connect them in serial, which is available in the market, 1 ohm and 5 ohm resistors, so you can introduce a 6 ohm resistors which is not available in the market. So this helps how? To find out non-standard resistor values in practice by using the serial connection. So this is another advantage of this equivalency concept. So when you come here, this is a new type of equivalency, but it starts with a serial connected two elements. Here are independent voltage source connected in serial with a resistor. We are saying that you can replace these two elements with these two elements. So black square inside circuit and blue square inside circuit. The difference is resistors are going to be the same values, but this independent voltage source voltage is going to be replaced with an independent current source, of which current is equal this voltage source voltage Vs over R. If you choose this independent current source value as Vs over R, then put that resistor connected to the terminals of independent current source. We are saying this RL load resistor current and voltage do not change because this black circuit inside and blue circuit inside, they are equivalent. So how are you going to prove that these are equivalent? All you've got to do is to calculate that IL in the first circuit and that IL in the second circuit. You're going to see that these two currents are going to be the same. And then, since these are the same, multiply those currents with the RL value, you're going to get the voltages are also the same. So that means this element, if you do the replacement of the equivalent circuits, the other elements current and voltages do not change, so these are equivalent. So the RL in these circuits are called load resistors, current and voltage do not change. Load resistor current and voltage do not change by using the equivalent definition. We said that. Independent voltage source replaced by an independent current source. Attention references, it says here. Why it says so? If you look at the first circuit, you have that independent voltage source current. According to passive sign convention, it is downwards, isn't it? But in this independent current source here, the current reference is upwards. So if you put that current reference downwards, then it won't be equivalent. So it's going to be a problem. So you've got to pay attention to that. serial resistors became serial resistor became parallel in here. So we are going to see the parallel resistors later on, maybe. Forget that information now. Number of nodes reduced. If you look at the left hand side, the number of nodes 1, 2, 3, and the right hand circuit we've got just 2. So one of the nodes reduced. What does this mean in mathematics? It is asked here. So the answer is easy. If you're going to, let's say you have a circuit, a given circuit like that, and then you're going to do the node analysis for this, node voltage analysis. So you're going to write these Kirchhoff current law equations for the nodes. So if you do this transformation, then the number of nodes reduced by 1. That means you're going to write less equations. That's the mathematical mean of it. If you look at this equivalency now, in this one it is different from the previous one, because in the previous one the equivalent element was in the same type element of the serially connected elements, but in this one it is not the same type. On the other hand, topology is changed. There is a serial connection here, but this is not a serial connection, and there is an independent voltage source here, and there is a different type of source here. So type and topology both change in this equivalency. This equivalency has a special name. It is called source transformation. The reason is that, so in the first circuits we've got a voltage type of source. So in the second one we have got an independent current source type. That's why we call it source transformation. So what we have seen here in the concept of serial equivalence, we have seen the serially connected resistors and serially connected independent sources with a resistor replaced with another source. The next we're going to see the parallel equivalency. So that is the end of this video then.